Okay, so let's get started. So first of all, first thing I want to do is, if you have any question, I will go over some things about the homework. So if you have a question on the chapter or anything like that, that would be a good time to talk about it. Yes.
So when we talk about GARP,
Yeah.
and we're talking about all the XTs,
Yes.
so we have some T which is equal to like 1 to T. I have a way that I want to think about it, but can I run it by you?
Yeah.
So essentially the way I'm thinking is if you have some consumer and their consumption per month is some XT.
Yes.
And so every month you have some consumption bundle, right?
Right, right.
And so maybe July is the month where they spend the most. And so therefore that would kind of be like their X star, like their greatest, where all the other XTs within that set will either be equal to or less than that.
Okay.
Can I think of it that way?
Okay.
Because then
You started okay.
Okay.
Now, why do we care which one is the largest in the sense of the vector?
Well, it doesn't matter which one's I guess the only reason why I'm saying we need the largest is because isn't that how we assume directly reveal preferences? And so if it's a preference that's always if it's some XT that's always preferred to the other X's, then that's the maximum value.
Okay. Now, you have two types of data for every month.
Mm-hmm.
Not just the purchased bundle XT. You also know what price vector was prevailing when that was purchased, and that's crucial.
Yes.
Because what X1 cost might be completely different than X2, even though some components of X1 are much bigger than the corresponding components of X2. I mean, it may be that in X2, the prices of these goods have fallen so much relative to P1, right?
Yeah.
That is why, in the definition of GARP and everything we did in that section, the PT and the XT go together always, right? So, like I said in class, the only thing you can do with that information, which ends up being extremely impressive for how far you can get with that little thing, is you can put the goods here, and every time you have an XT, you also have some prices. From those prices, you will know the budget line that's perpendicular to the vector PT, which then, if it passes through XT, that is then the set of all the bundles that cost exactly as much as XT, right? And everything below costs less than XT at these prices. So then the idea is to say, okay, suppose that in XT plus 1, they bought this, right? Mm-hmm. Perhaps they were facing these prices. I'm just making an example, right? So now what you know is, look, at time t, not t plus 1, at time t, this person could have purchased xt plus 1, but they didn't. Okay? So xt has been directly revealed preferred to xt plus 1. But you can make absolutely no statements whatsoever of any interest if you leave the prices out. Here, we do not observe the income. We observe what the person spent. And in order to figure that out that's not even a direct observation. But we can figure it out by taking for each good that the person bought, how much they bought at what price, right? So it's the PX product, PTXT product. Okay? So that's the basic idea. Meanwhile, at pt plus 1, we cannot really say that xt plus 1 has been revealed preferred to xt. First, that would be really strange, because earlier xt was preferred to xt plus 1, directly revealed, right? Furthermore, however, at time t plus 1, at those prices, xt wasn't even affordable. Okay?
Alright. So,
Make sense?
Yeah. That
Okay.
makes sense.
All right. Any other question from the chapter? Okay. So what I did last night was I put up a little 2-page document that should at least get you started for the homework. And it also had some elaborations for the previous homework. All right? I want to say a few words about that for the previous homework. I really want to see an explanation of what you do. If the explanation involves multiple graphs, give me the graphs, all of them. For example, we had preferences like that with a max preference, right? I forget which number it was. So I indicated here that, if the budget was like this, then your maximum is right here, right? And so when you answer that, give me all the other options, right? What if the budget was like this? Like this, right? Then the maximum would be there, right? So when you answer, try to explain it. Pretend you're actually teaching an undergraduate or a graduate student. I don't care who you're teaching, but I want to see that you know the logic of it. Yeah. So explain in that way. And if in the course of working on it you don't see how to do that, well, that's when you ask me. Okay? Now, a lot of the homework that's coming up is, I'm going to give you hints and starts today, in fact, in that document. So that's hopefully a little easier than last time. Now, I want to say one more thing about this. Immediately after that problem, there's another one with the indirect utility function exactly the same, right? And then he says, can you come up with a simple quasi-concave utility that had that indirect utility function? So this direct utility function, the max of x1, x2, is, in fact, one utility function that has the same indirect utility function. Was it v over the minimum of, or whatever it was, I don't remember. But it was that. But that's not quasi-concave. So you could say, oh, I could use this, but when you see the upper contour set of a typical indifference curve, right, it's not a convex set. We see that? If you take a point here and a point there, you step outside the set. Right? So that is why the answer, without explaining at all, the answer Varian gives is just the x1 plus x2 indifference curve. Because that one is quasi-concave. Okay? All right. So I want to leave that now. I want to leave it, and I want to go over some of the problems that are coming up. When I said I know the answers are floating around on the web, I wasn't kidding. That's where I got them too. So I highly recommend the following. Of course, if you look at them, you must tell me on the homework. Of course. I highly recommend not looking at them unless you really, really, really got stuck. So I'll try to get you started on every problem so that will not become an issue. So let us look at problem 8.1. And did everybody see the document I uploaded last night at 9? Okay, good, good, good. So what I'm going to say probably has a lot of overlap with that, but here I am, and so this is a chance for you to ask me further. So the first 8.1 says, Frank Fisher's, that's actually a little bit of an in-joke, because Frank Fisher was a legendary MIT economics professor. I don't know what the story about the jokes is here, right? I just don't know. Frank Fisher is a previous generation economist to me, and I didn't interact with any of his students to know why this is here. So let's say jokes is a good. Notice what we're assuming here. This is just a little aside. Not all jokes are equal. I know that very well. Some of them are just not funny. And they're unequal to different people. Some are funny for others and not funny for you, and so on. If we're going to pretend that the good called a joke is measurable by a real number, what are we assuming? All the jokes are of equal quality, and such a thing as 0.96 of a joke makes sense. And it gives you a little less utility than an entire joke, even though it might be missing the punchline. Why am I saying this? This is, of course, just a little exercise, right? But when later you want to apply what you learn here, think about what you assume about the goods, right? Okay, enough of that. So he says the demand function for jokes is xj of pm, where p is a vector of prices. So there are prices for the jokes. There's a price. Okay, fine. Maybe he will go and pay per joke for a stand-up comedian, and then walk away after a joke when he thinks that that's enough money for jokes tonight. That's also not how jokes are sold, right? I mean, typically, if you want to go to a show, you will go to the show, and you pay a ticket and see the whole show. All right. So, but now we're pretending he's paying per joke. And if he consumes 0.6 of a joke, he will pay 0.6 of the price of the joke. Okay. So we have a positive income, M. We have then what the exercise asks you to do is, in fact, a big hint. Suddenly you see there is an expenditure function. And you have a second order derivative of the expenditure function, right? With respect to PJ, and the utility level. What do we know about the expenditure function? Those identities and everything we learned in chapter 7 are going to come back and back and back, and they're very useful, all right? So the partial derivative of the expenditure with respect to the price PJ is the Hicksian demand. Well, then suddenly you realize, but now we're talking about the change of the Marshallian demand with respect to income, right? Slutsky equation. Because the problem gives you, I'm trying to tell you how you would discover how to start, right? Rather than you look it up and you do what he says. So you should always try to just read it very carefully and say, okay, what does he really say here, right? So you be like a detective. You solve a case, you find clues, right? And then you say, what do I know? I know the Slutsky equation. I know the expenditure and the derivative of respect to the PJ is the Hicksian. I want something about the income, so I can't really rely only on the Hicksian demand function, which does not have income as an argument, right? But I can rely on the Slutsky equation, which at least connects the derivative of xj with respect to m and the derivative of the Hicksian with respect to pj. Right? Once you get that far, the exercise becomes practically trivial. So that's what makes lots of these exercises difficult. So be a detective. Always there is enough information to get you through. With the exception, which annoyed me again, when I discovered that 8, but I put that in there.
8 point. The one with the inferior group.
8:15. Yeah. We didn't actually yet talk about labor supply. It's in the next section, next chapter. So read that first, because otherwise 8:15 is really impossible. But at least I got it in good time. All right, so 8:1, all I'm going to tell you is this, but always use this advice for any exercise. There's always going to be, trust me, enough information on the exercise, but you have to have in your mind all the identities, everything you've learned that might be usable. And you go and pick. It's like you have a supply closet in your mind, right? You open it up and you find the things that will help you in the scavenger hunt that is exercises. And then you do some algebra. You'll never have to do amazingly difficult math, right? The hard thing, but the only substantial thing you have to do, is to figure out what of the things you learn is applicable and then do it. Okay, the next problem we have, I have assigned is 8.5. So for that, we have a straightforward Lagrange approach to maximization, right? So that one, I'm treating as an easy problem, right? Some of you have explicitly done these things, for example, in mathematical economics. And if not, he explains at the end in the appendix how to solve it. So when you all meet, I know you're all meeting tomorrow, then those who know help the others to set up the Lagrangian. All right? Do check the second order condition. It will be fine, but do check it. Even though the answer doesn't really go as far as that. You always want to check the second order condition. Why is that? Because what if you accidentally did not find the maximum, right? 8.6 is a variation. Instead of prices that are actual numbers, you have them as parameters, P1 and P2. The utility function is slightly different, but they're both Cobb-Douglas. So in fact, you know the Cobb-Douglas. You've seen it. It's in the chapter as an example at the end of chapter 7, I believe. So it is entirely okay, legitimate, to use that, refer to that, but I'm telling you, add the check for second order condition, which he doesn't. He doesn't because he knows Cobb-Douglas is quasi-concave, so the second order condition will be satisfied. But I want you to get practice in setting up the boarded Hessian and seeing how it's calculated and confirm to yourself, yeah, look, it's always of the correct sign, and therefore this is a quasi-concave utility function. Okay? Am I talking too fast? Are we okay? Yes? Okay. I will not promise to be on the other side of an active email or Skype tomorrow, but I will be keeping an eye on it. So if you have some really pressing questions, send an email and we'll see if I'm able to answer. 8.8. I want you to look at 8.8 and 8.6. And I contend that if you've done 8.6, there is very little work that you have to do for 8.8, except to make a good observation. What do you see between the utility functions of 8.6 and 8.8?
They're just a monotonic transformation.
And what do we know about the demands? Does anything change in the demands? Okay. So if you explain that in a coherent sentence or two, correctly stated, that's enough of an answer in 8.8.
Okay.
Don't copy the one sentence that he has in the answer. Just write it in your own words, right? This is one case in which I really don't want you to look at how he wrote it. I want you to express it. Because that's all there is to it. Okay. 810 is for the PhD students, right? I will say,
and that's one that I'm like
okay, all right,
really
okay.
having trouble with.
I'm gonna start you off with a picture,
Okay.
right?
Yeah.
And I will explain something that will help,
Okay.
and I'll leave it at that. I believe what I'm going to say is enough so that you don't need to go look at his answer.
Okay.
So anyway, that's my hope.
Okay.
So here's what I'm going to do. The important difference between everything we've done so far and this one, and everybody, even if you're not in the PhD, remember you can do, for bonus credit, you can do the PhD problems. And so I recommend trying at least. Up until this point in time, we looked at the case where the income was a given amount of money. It was exogenous, it was an amount of money, right? But it came in the form of money. Here, that's not the case. In fact, the fact that the X1 and X2 are consumptions in period 1 and in period 2, that's just a question of interpretation. The analysis doesn't really differ from what we saw before. It doesn't differ because of the intertemporal interpretation. The math is the math. I don't care how you interpret it. As long as you realize, like with the jokes, that the interpretation sometimes is forced. But he tells us explicitly that we have endowments. He's going to have so much of one good and so much of the other, right? So we need to figure out how we are going to draw the budget line and how the budget line will be changing when the price changes. And why do I care about the price changing? Well, I care about it because he's talking about the Slutsky equation, the first thing, right? So, this point with coordinates x1 bar and x2 bar is the person's endowment point. It is going to stay. It is exogenous. The budget line for any price vector must pass through this point. So this is going to be the point from around which the budget line will tilt when the prices change. Right? So this is not the case where one of the intersections with the axes in everything else we've done before, when a price changes, one of the intersections with the axis of the budget line stayed the same, right? Not true here. This will stay the same, and the budget line will swivel around it. Why does this stay the same? Because no matter what the prices are, this is affordable. The person has it, right? The point is, I have this thing, and I can go to the market and sell a bit of one of the goods to buy a bit of the other. You might remember this if you had international economics ever, where a country that trades in the world, it has what they've produced treated as an endowment, right? And you have a production possibility frontier that curves down. You probably have seen that in some class. And then when you trade with the world, you actually have prices. For a small country, you have to take them as given. That's the story. Except it's not the country here, it's a person in this story, in this exercise. So, you will draw a budget line, but you're not going to make it pass through particular intercepts. You will make sure that it has the correct slope by being perpendicular to the vector of prices. And you are going to make sure it passes through the endowment point. Okay? Okay. Once you figured out where it needs to be drawn and how it will swivel if a price changes, now you can do your maximization and so on, right? So, yes?
Or just okay.
Yeah, okay, that's fine. Suppose then we do our standard story, right? And you will find that our friend chooses this point. It doesn't have to be the endowment, right? It could be, but most likely it won't be, right? That's why people go that's why people go to the market, because they want to trade in some of the stuff they have to buy some more of some other stuff. So if this is the case, what are they selling? They're selling X1, right? Because they'd like to have more X2. In fact, you can see how much. They're going to sell this much of X1 in order to buy this much of X2. Okay? Now I would like to point out that, so did that sit down okay, or do you have any questions on that? Okay. So I would like now to point out that the utility maximization problem looks just as before. It's like max with respect to the x vector of the utility. I can write this out. Why not? Subject to P1x1 plus P2x2 equals P1x1 bar plus P2x2 bar. Okay? Instead of M. Notice now, we don't have the parameter M. The income of the person changes when a price changes. Right? But what is this? The value of what the person has. Right? It's the value of the endowment. And that is what he can spend. Right? Okay. Now, I would want to rewrite this now. Instead of, this is the expense, and this is the income, right? I will write it as net expenses, because then it will make finding the dual problem, the minimization of expense, net expense, will make it clear. And once you have that, I will leave you to your own devices. Okay? So, I'm going to do the following, not particularly mathematically impressive substitution. Okay? So, I will also interpret it for you. Okay? So all I did is I moved everything from the right-hand side to the left, and I combined the terms that have the same price in front of them. That's all. So now, what is the story? What do we have here? This is the net income from purchases or sales of X1. It could be positive or it could be negative. In this particular case, it's positive, right? Because the person is going to consume less than they own of X1. So this is going to be, this is going to be negative. I moved it in that side, yeah. As an expense. It cuts down on your expenses, right? It's negative expense. So for this particular case, this one is going to have a negative sign. This one will have a positive sign because you spend more to buy a bit more of X2 than you already owned. Okay? So use this, use this formulation as the expenditure and then minimize that given that you have a particular utility function, utility level that you wish to reach. Once you have that, and since this is the way I defined it, this is the net expense, that is exactly how I should define it because then I'm talking about minimizing it, right? So the problem that you set up to write down the expenditure minimization is minimize this with respect to the constraint that the utility function is equal to some given number u. Then follow the same process that he follows in the chapter to derive the Slutsky equation and all the other stuff, but with this formulation of the problem. Okay? And that is actually probably the most useful thing from this exercise. You can use it for international trade, or here, it's a person who's a lender or a borrower. If X1 is really today, and X2 is tomorrow, or next year, whatever, right? Is this person borrowing or lending? Lending, right? She lends this much, well, this much in dollars, in order to then consume more next period. In macroeconomics, very soon, you will be seeing how you can write the P2 as an expression involving the interest rate. But this is at the heart of it. This is how you think of it. Is everybody understanding this? Any questions? Okay. So that's it for 8:10. That's the time. 11:34. Yeah. I was aiming to spend just an hour today, so I think we'll manage. What's the next one? Is 8:11. Yes. Okay. So in 8:11, we have a consumer who's demanding two goods, and they tell us just two. So they have the PT and XT information for just two different T's, period 1 and period 2, or one occasion and another occasion. All right? And they ask something, it says the price is so much, so he demands this, or the prices are these, and then he demands that. Is this consumer maximizing utility? How would you approach that? This is actually a very easy problem if you understood revealed preference. So I'll leave it at that. Right? Check GARP. Is it satisfied or not? That's all. Everybody okay with that? Amy, Tiffany, Shunyu? Okay? Questions? Okay? All right. The next one is, this might be it for the MA, or what else is there? I should have.
I think 8.13.
Yeah, there's
8:13, okay. Yes. The utility function is, okay, let me start it. Once I start drawing indifference curves, the rest will be easy. So I'll leave it to you. Make a system of axes here. And let me write down the utility function, which is u of x1, x2 equals the minimum x2 plus 2x1 x1 plus 2x2. Okay. All right? Before I do anything, I want to think again like a detective. Have I seen anything like this before? The answer is yes, of course. But it looked simpler. Min of x1, x2. Perfect complements, right? Leontief utility function. Right angles. Aha! So what do I expect? I expect some sort of corner. I expect that the utility function is not differentiable. But at this point, I might not have any idea what it looks like, right? Okay, how do I solve that? Let me choose a utility level and attempt to draw the indifference curve that passes, that is at that level, right? This is how we'll proceed. So, choose some utility level, let's call it u, like he does all over the place. So, I choose a number, right? You want to actually do it concretely at home and call u to be 10, fine by me. All right? So, then I'm going to set both of these equal to u separately. So I'm going to decompose this. And I'm do this first equal to u, this then equal to u, and draw the lines. They're going to be straight lines. It's not that hard, right? So let's do it. So first I set x2 plus 2x1 equals u. Actually, why not make this u to be the number 10? But it could be any u, right? Okay, so that is equivalent to x2 equals 10 minus 2x1, right? And so what are the intercepts? If x1 is 0, x2 is 10. So it will pass through this point, right? Remember, straight line, you need just 2 points. So find the intercepts is the quickest way to draw it. And if x2 is 0, then x1 is 5. So from the first part here, we get this line. Now we have to do the other one, right? Okay. Now, as you can see, all that happened here is a flip between x1 and x2. So I'll skip the actual calculations, and I'm going to draw it here. Okay? Now I want to show to you the upper contour set at that utility level. That is, all the points that achieve utility equal to 10 or more. I'm going to shade something, and I'm going to let you verify when you study later that this is the correct thing to shade. How? Well, so I'm going to shade it like this. So it's like a perfect complements, but it kind of spreads out and is not at right angles. Okay? Now, why does it work with a minimum here? Why did I shade it like that? There is a number of ways to test it, right? So I'm not going to do it, but I'm going to tell you how to do it. Choose points here, a point here, for example. That's here. and calculate the utility by plugging the numbers here. Right? It should prove to be 10. Do the same here, any point on this segment. Then choose a point here, because why do they leave those segments out? Put it in the utility function and see what number you get. Put explicit points there, put coordinates, right? I think that's the best way to convince yourselves this is the upper contour set. Once you have that, I think the rest is actually fairly straightforward by continuing with the graphic. So, okay? So I'm not going to say anything else. Well, I'll say this. This point is going to probably be kind of interesting. Let me draw a couple, let me use actually another color to draw some possible budget lines. Possible, right? If the budget line has a slope kind of like that, then you're going to find that the maximum is at the corner, right? But it is entirely possible that, for example, good 1 is relatively so much cheaper than good 2 that you buy just x1 and you have a corner solution. And once you understand that, you can do the same the other way. And it asks you to figure out at what price ratio do you switch to buy only x1, and at what price ratio do you switch to consume only good 2. Okay? So this is really all you need to do for this one. It's mostly geometry, mostly understanding what the deal is, and this is sort of complements, but not perfect complements. For the range of prices between the extreme prices that make you go to a corner, you don't move, right? You're always at the corner, but if one of the goods becomes significantly cheaper, then you buy only that. Whereas in the perfect complements case, it didn't matter what the prices were. You always bought the same amounts. Okay? All right. 813. What's next? 814. This is actually way easier than it might look. There's 3 goods, right? So, and look at the form of the function. What does it look like? Cobb-Douglas, right? So, in fact, you know what the demand functions will look like. But with 3 goods, well, I mean, how hard is it, right? You know how to do it. So, the second part is interesting. So, the first part, part A, it will be valid to just do the Cobb-Douglas demands as long as what you get for S1 or is it S2?
S2. Or
yes.
The IRA.
Right. So if the answer you get from part A for S2 is less than L, then it's valid.
Okay.
If it's bigger than L, then oops, you've hit the other constraint. So this essentially, I can't draw it because, I mean, I could try, but it's in 3 dimensions, right? So here we have a second constraint, right? But it's easy, you just do, I mean, you could do the full Karas-Quinn-Tucker. You know how to. But, right? But it's actually quite simple because it's very logical here, right? If you hit for S2, so if you would like to do more than L, according to what you calculated from part A, then the law restricts you. You cannot consume S2 more than L. So just put L there in S2, and suddenly you have a reduced problem with just 2 goods, and L is treated as a parameter. Okay? Is there one more? 816. Well, 815 I told you what to do. Go a few pages further and just do it. It's not that super difficult if you read ahead. And then the last one, 816. use very logical thinking. And notice, however, we have a little difference here. We do not know the form of the person's utility function. They do not give us the formula, right? So, but we know there's two goods. The person has strictly convex, strictly monotonic preferences. So the indifference curves will be curves. They will not be sharp points because they're differentiable, right? And they're thin because it's strictly monotonic. So it's your most well-behaved utility function you could have, right? Then they tell us that the person has M income every year. So currently the person is consuming is like X1 star, X2 star. So we're going to immediately say, okay, right now the X1 star, X2 star is at the point that looks like I have to erase the red really well because it stays longer on the board. Okay. So all you know, and the numbers go here, is there's going to be a budget, and you're going to be in a situation like this. So start with this picture. Then it tells you more. Consumer has income M every year. The current level of consumption is this. And he tells you that X1 star and X2 are positive, which is why I chose them to be positive. So this person is not at the corner solution. So next year, there is an interesting thing because now, next year, the person gets a grant of amount G1, which is less than or equal to X1 star. So an amount that will be somewhere here, but that has to be spent explicitly only on good one. Okay? So I want you to think, what does this do to the budget? This is not going to stay a straight line budget line. For those of you who have the Netsuba book, he has an excellent discussion, an entire chapter about budget lines and budget lines that are multi-pieced and so on. But think about it. What this tells you is that your budget shifts up by an amount, in terms of good too though, that will make it possible for you to consume some level of X1 here. But why does it jump up that part? Because we tell the person, as long as you're purchasing in this area, we're going to give you extra money. Right? But you can only spend it on that good. Did I draw it right? Did I cover properly that you can only spend it on that good, or did I not do it right? I'm not going to tell you. I want you to think about this, and I want you to draw the correct budget line and convince yourselves that you did. And then follow that kind of logic for the rest of the problem. Okay? What's clear is that if the person consumes something less than X1, if the person takes the grant, right, then the person can consume more of good one. What I did was I tried to show you that there'll be more, effectively more income. Is that the right way to do it? Argue it out among yourselves, figure it out. Okay? Okay. This is it. Do you have questions for me? Anybody? Any questions? Okay.